Hi everyone, in this video I'm going to present an outdated fact detection method for knowledge bases. This is the outline of my presentation. I will first give the motivation. Knowledge bases such as DBpedia provide rich structured information of real-world entities and their relations, which can greatly increase the performance of many applications. However, the facts in knowledge bases may become out of date as the world changes. For example, a few days ago, we visited the DBpedia homepage and looked up the facts about the NBA star Kevin Durant. We found that the current team of Durant is still Warriors in DBpedia, even after he signed with Nets in 2019. This piece of information is outdated, and this is just a microcosm of the entire knowledge base. Then, a practical problem is how to detect the outdated facts in knowledge bases. A commonly used method is to extract some up-to-date facts as reference data from news, media texts, and encyclopedia websites, and to detect outdated ones by comparing with the facts in knowledge bases. However, purely relying on the reference data is not enough, because they can only cover a small proportion of the knowledge bases. Naturally, we should generalize the information from reference data by rules, machine learning model, or involve human to collect more evidence. However, there are two main challenges to tackle. First, it is not trivial to build a well-performed model for outdated fact detection. And the second is question selection for user needs to consider two criteria, informative and diversified, to maximize the number of outdated facts that can be detected. Our contributions are summarized below. We propose a novel human-in-the-loop framework to detect the outdated facts in knowledge bases. We build an iterative classification model to predict the outdated facts. We judiciously select questions iteratively for human to verify the candidate outdated facts. We conducted experiments on real KBs to show the performance of our framework. Now, I will give the formal definitions of our problem and related concepts. First, we figure out what is fact. A fact in the knowledge base is a triple, where S is an entity, O is either an entity or a literal, R is a relation or property between S and O. For example, Kevin Durant and the Warriors are entities and their relation is current team. This URL is a literal and it's a property of Warriors. A fact is outdated if it is not synchronous with the changes of the real world. As we said before, the first fact is an outdated fact, but the second is not. We aim to leverage human to collect information in this work through the human intelligence tasks, which is specially referred to the task for a fact that asks human to indicate whether it is out of date or not. Here are two examples. Next is the logical rule, which is formalized as A inverse H, where the body A is a conjunction of atoms and the head H denotes a single atom. Each atom corresponds to a triple that has variables as the subject and object position and with a fixed relation or property. If all variables in a rule have been substituted by specific entities in the knowledge base, it is called an instantiation of the rule. The semantics of logical rule is used to infer more outdated facts. If all the body's instantiations are up to date, we can conclude that the head's instantiation is up to date. Based on the inverse and negative proposition, we can conclude that if the head's instantiation is outdated, there must exist one outdated triple in the body's instantiation. Remember that the former instantiation tells us that Durant and Curry are teammates if they are all in the Warriors. Then, if Durant and Curry are no longer teammates, we can conclude that one of them have left the Warriors, but we don't know who. Actually, if the rule only contains two atoms, we can safely infer that the body's instantiation is out of date. Now it's time to give our problem statement. Given a KBK, a set of reference facts T, and a budget B that determines the maximum number of hits answered by a human. We aim to detect the maximum number of outdated facts in K. Next, I will introduce our framework. The framework contains 3 phases. The first phase is outdated fact prediction, which aims at predicting outdated facts using an iterative classifier model. The output of the model is the likelihood of each fact being outdated. The second phase is human-based verification, which is to verify the outdated facts detected by the ML model as many as possible within the given budget. The third phase is rule-based fact expansion, which aims to expand the human answers to detect more outdated facts. I will introduce each phase specifically in the following slides. In the first phase, we try to build a classifier to predict the likelihood of a fact being outdated. We notice that many facts in the knowledge bases never change, which are called inactive facts, and will not become outdated. An inactive fact is generated due to an inactive entity or relation. For example, all facts related to Albert Einstein are inactive facts, and Albert Einstein is an inactive entity. Birth date is an inactive relation since the objective entity of this relation never changes, no matter what the subjective entity is. Only active fact may become outdated, which has active entity and relation. Thus, features should be extracted to detect active facts. For each fact in the training example, we generate its features based on the current and previous versions of KBs. The first 3 features, the completeness of entity S, historical update frequency of entity S, and the number of links from other entities to entity S, are used to determine whether the entity S is an active entity. The last 2 features are the historical update frequency of the relation R with entity S, and the time of existence of the entire fact, which are to determine whether the relation R is an active relation and whether the fact is an active fact respectively. To start training the model, we need some training examples. Given an up-to-date fact from the reference dataset, if it has already been in the knowledge base, it can be used as a negative example. Otherwise, we check these 3 kinds of triples whether they are outdated or not based on the correspondence of the relation. Here, the asterisk is a wild chart. For example, if relation R is a one-to-many relation, then any triple with relation R and objective entity O is out of date and can be used as positive example. Then we aim to leverage the users to verify the facts predicted by the ML model in the second phase. The biggest challenge is which key facts should be asked in each iteration because it directly determines the number of outdated facts detected, which consists of verified by the users directly and inferred by the rows. Here we build a graph model for this problem. Each vertex V is a fact in K, and its weight W is the probability of V to be outdated. A directed edge from vertex U to vertex V indicates that U and V exist in the right and left hand of an instantiation of a row respectively, which means that if U is out of date, it can be inferred that V is outdated or very likely to be outdated. Then the top K best hits selection problem can be formulated as follows. WV denotes the weight of vertex V, which is the probability of V to be outdated. Maximizing the total vertex weight can maximize the number of outdated facts in K hits. DOV denotes the normalized out degree of vertex V. Maximizing the total vertex out degree can maximize the number of outdated facts can be inferred. The above 2 goals may not be reached at the same time. Thus, alpha and beta are used to balance the weights of them. The constraint means that the set of K hits must be an independent set. The reason is that if asking U can deduce the answer of V, it is wasteful to ask both. Then, selecting the top key best hits is equivalent to finding the maximum weighted key size independent set in the graph model, and we can prove that it's NP-hard by a reduction from the 3SAT problem. However, enumerate is time-consuming and an efficient greedy algorithm is needed. The traditional greedy strategy is to choose the vertex with higher weight and smaller degree to maximize the total vertex weight of an independent set. But in our problem, minimizing the degree of a vertex will lead to a reduction in the number of outdated facts can be inferred. Thus, we prefer the vertex with larger weight and smaller in degree at each step to reach a key-size independent set as fast as possible. After collecting user answers, all verified vertices and the corresponding edges should be removed from the graph model. Meanwhile, we should expand more outdated facts based on the semantics of logical rules. That is, given an instantiation of a two-atom rule, U in first way, if V is outdated, U is also outdated and can be safely removed from the graph model. Meanwhile, if U is confirmed to be up-to-date by the user, we can also infer that V is up-to-date and also remove vertex V from the graph model. Consider a three-atom rules instantiation U and Y infer V. If V is outdated, it is hard to determine which of U and Y is outdated, but we can update the weights of these two vertices for further deducing. Then I will show you some experimental findings. We used two real-world knowledge bases to evaluate our method, Yago and DBpedia. We detected the outdated facts in these four versions shown in the slide was considered as a ground truth respectively. We choose the above versions of knowledge bases since we can only obtain the news data from the GigaWorld V.5 dataset for that time period as a reference data. We used the named entity recognition tool to identify the KB entities and open NRE to extract relations. We compare the effectiveness of our framework with USB, which extract hot entities from the reference data and then crawl their encyclopedia websites to obtain the latest facts for outdated fact detection. We recruited 10 students who had necessary skills to answer the questions to take part in the evaluation. Before starting, we generated some hits for qualification test. The correct rate of each participant was recorded for further use in answer aggregation. In these experiments, we took precision and the number of outdated facts correctly detected as evaluation metrics. The first two figures show that the precision of our algorithm in two datasets was higher than 0.9, which means that most of the outdated facts confirmed by users and inferred by rules were truly out of date. The precision of USB didn't exceed 0.6 since the facts of entities that appeared in the news and their linked entities didn't necessarily change. In the following two figures, we can say that at the rise of budget, the number of outdated facts we correctly detected also increased. When the budget reached 3,000, it had exceeded the number of outdated facts detected by USB, which bore out the claim that purely relying on the reference data is not enough because the news can only cover little. In the end of the video, let's summarize our work. We have proposed a novel framework to detect the outdated facts in the knowledge bases. We have built an iterative outdated fact prediction model to provide the likelihood of each fact being outdated. We have judiciously selected questions iteratively for the user to verify the candidate outdated facts. We have also utilized the logical rules to deduce more outdated facts. We have demonstrated the effectiveness of our approaches on real knowledge bases. Thanks for your listening.